We've talked about how functions can fail to be continuous, so the next natural step is to talk about how a function might fail to be differentiable. There are many things that can go wrong, but these things can be broadly categorized into three categories. The first is a failure of continuity. We've learned that a function which is differentiable at a point A must also be continuous there. Hence, if a function fails to be continuous, it cannot possibly be differentiable. I'll graph a typical function on the left here so we can see what goes wrong. If we try to draw the secant lines, note that they don't seem to be converging to a tangent line, and that's an issue. To see this more concretely, let's look at the function which is 1 minus x squared away from 0 and 2 at the point 0. This is basically what I've drawn above, and it's certainly not continuous at 0, hence it should also fail to be differentiable at 0. Evaluating the limit of the difference quotients at 0, we are left with this limit. The numerator converges to a finite number while the denominator goes to 0. Hence, this limit does not exist. The next failure is when the limits are infinite. This corresponds to either vertical tangents or what we call cusps. The problem with these functions is that geometrically, the slopes of the tangent lines are vertical, which means that our limits don't exist. So there are really two cases here. The first are functions which are nicely behaved, but for just one moment point straight upwards. The usual example of this is the function x to the power of 1/3, which when we write out the difference quotient results in this. Left with 1 over something which goes to 0, we again have a non-existent limit. The other case is a badly behaved function whose tangents are still vertical. An example function is x to the 2/3, which is similar to our previous example, albeit a little different. Doing the limit computation is almost identical to that above, and once again results in a limit which does not exist. The final type of failure is a corner. Differentiability is defined using a two-sided limit. Hence, the limit can fail to exist if the two one-sided limits both exist but fail to agree. This will appear like a corner in the graph of the function. Now, we've seen functions like this before. For example, the absolute value function. If we compute the one-sided limits of the difference quotient, we're left with these absolute value of h divided by h terms. And we've seen these limits before, right? With a result of +1 from the right and -1 from the left. Thus, the limits don't agree, and so the limit doesn't exist. This captures all the ways that a function might fail to be differentiable. We see that it often comes down to when the graph of the function fails to be smooth and contains a sharp edge or possibly a gap.